Welcome to Important Taylor Series and Properties. So recall, we previously saw that e to the x was equal to its Taylor series or Maclaurin series. So e to the x was equal to the sum from n equals 0 to infinity of x to the n over n factorial. It would be very nice to have more known series for functions. So we will now see more common Taylor series. So here are some important Taylor series to keep in mind. We'll just run through a variety of them. We'll start off with our e to the x. E to the x, again, is the sum from n equals 0 to infinity of x to the n over n factorial. So that is just 1 plus x plus x squared over 2 factorial plus etc. And this converges on the entire real number line from negative infinity to infinity. Sine of x, if you think about sine evaluated and its derivatives evaluated at 0, right? All of the sine components of sine derivatives will go to 1 or negative 1, alternating. And then anytime we land on cosine, that will go to, all of the ones that land on sine will go to 0. And then the ones that land on cosine will go to either plus or minus 1. And so what we wind up getting is we get a sum from n equals 0 to infinity of negative 1 to the n. There's that alternating sign from whether cosine is on the positive or negative. But then we only have x to the 2n plus 1 over 2n plus 1 factorial. So this is saying, well, sine of 0 is 0. And so anytime you're on a derivative that is just a sign variation, we're going to get 0. So the even derivatives are all 0. This again converges on negative infinity to infinity. Cosine is very similar. It's just that it'll be on the odds that go to 0. And so we get the even terms in our series. We'll have the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n over 2n factorial. Again, this is on the entire real number line. Next up, we have natural log of x. Doesn't make sense to do a Taylor series at 0 for this, since natural log is undefined there. Instead, we do the Taylor series at 1. And so we have the sum from n equals 1 to infinity of negative 1 raised to the n plus 1 times x minus 1 raised to the n all over n. This is defined on the open interval, well, on 0 to 2, 0 not included, 2 is included. Next up, we have 1 over 1 minus x. This is simply the sum from n equals 0 to infinity of x to the n. This converges on negative 1 to 1, the open interval. After that, we get our what they call a binomial series. So here we're looking at 1 plus x to the k, where k doesn't have to be an integer, right? So k can be any real number. Then this series winds up being the sum from n equals 0 to infinity of k times k minus 1 times all the way down to k minus, in parentheses, n minus 1. And we divide all of that by n factorial, then times x to the n. So again, this allows us to say, write the series for the square root of 1 plus x, or the cubed root of 1 plus x. This is on -1 to 1, where the convergence on the ends depends on k. So the convergence at -1 or 1 depends on k. Right. And then last up, we have tan inverse, or arctan. This Taylor series is the sum from n equals 0 to infinity of -1 to the n times x to the 2n plus 1 over 2n plus 1. So once again, all of the even terms cancel out and we just have our odd terms. And we get our alternating sign. Note, if we scroll back up, this looks very similar to sine of x, but sine of x, we had a factorial in the bottom. Tan inverse, there's no factorial. This one converges on the closed interval from -1 to 1. So here we have a variety of Taylor series for sort of very common, famous functions. So now we can sort of play around with these series to build other series. So let's suppose that f of x is equal to the sum from n equals 0 to infinity, a sub n, x to the n, and g of x is equal to the sum from n equals 0 to infinity of b sub n, x to the n, converge absolutely for absolute value of x less than r. Then we get some nice properties. So we have first our sum or difference rule. So if we want to express this Maclaurin series for f of x, either plus or minus g of x, this is the same thing as just adding or subtracting the term by term of the Taylor series. So this is the sum from n equals 0 to infinity of a sub n plus or minus b sub n times x to the n for absolute value of x less than r. So essentially what we have here is that we can add Maclaurin series term by term. And we have equality on the smaller radius of convergence. So, and we have equality. Oops, my pencil's not working. One moment. All right. So now that my pencil's working again, we can add the Maclaurin series term by term. And we have convergence on the smaller radius of convergence. Next up, we have taking a product of Maclaurin series. So if we wanted to take the product of f of x times g of x, this is the same as multiplying the sum from n equals 0 to infinity of a sub n x to the n times the sum from n equals 0 to infinity b sub n x to the n. We can essentially treat this like multiplying polynomials. This winds up being the sum from n equals 0 to infinity. We would have a sub 0 times b sub n. That would be x to the 0 times x to the n would give us an x to the n term. Similarly, the a sub 1 times b sub n minus 1, that would be an x to the first power times x to the n minus first n minus 1 power, would again give us x to the n, all the way up to a sub n times b sub 0 would be the other combination for getting x to the n. And this is again for absolute value of x less than r. So we can essentially treat it like multiplying polynomials. We can look for all the combinations that will add or multiply to x to the n. Okay. Finally, we have composition. So if h of x is a continuous function, then we have that f of h of x is simply equal to the sum from n equals 0 to infinity of a sub n times h of x raised to the n. And this is for absolute value of h of x less than r. So essentially, as long as we are looking at a interval where the range falls within of h of x falls within the radius of convergence, then we can just compose the function in the series. Okay. So in the next video, we will take a look at how we can use sort of these properties along with the basic series we have to develop, find other desired series.